Okay, take like 9,000. So, hi guys. I found a new way to record videos, so hopefully you can actually hear me. And I have a pen to write with now, so my drawings are going to be a little bit better. No promises that they're actually going to be good. I definitely need practice with it first. But yeah, we're gonna get right to it and start talking about redox. And in order to understand redox, you really need to know, going back to our first unit on the atom, why elements are electrically neutral and what it means if they're positive or negative. So let's take a look at the periodic table. Okay, so I'm going to start by drawing the hydrogen atom, and we're going to draw the nucleus of the hydrogen atom. Hydrogen has one proton. You can see that because its atomic number is 1. And it has, and I'll just draw a little plus P for proton. Protons are positive. And it has one electron, which you can see because its electron configuration is also 1. So in the orbital surrounding the nucleus, I'm just going to draw a little E minus. Hydrogen actually doesn't have any neutrons. And the way I know this is because its atomic mass of 1 minus atomic number of 1 gets you 0. But neutrons are neutral, so they don't actually matter for this unit. So we're going to ignore neutrons altogether anyway. So we have one proton and one electron. Because protons are positive and electrons are negative, and there's only one of each, their charges cancel. So hydrogen by itself is a neutral atom. If we look at another element, let's say fluorine, fluorine has 9 protons, and it also has 2 and 7 make 9 electrons. It has 9 electrons also. So fluorine is also neutral. Even if we look at, I don't know, let's say sodium. Sodium over here has 11 protons, and it has 2-8-1 electrons, which add up to be 11 electrons as well. So all elements, doesn't matter who you are, if you're on the periodic table and you're not bonded to anything else, you are neutral. What happens is when you take that element and bond it to somebody else, things change. So I'm going to take hydrogen and bond it to fluorine, and we're going to see what happens. So fluorine is more electronegative. Fluorine is the most electronegative element on the periodic table with a value of 4.0. And hydrogen is less electronegative with a value of 2.2. What that means is that fluorine really wants to have the electrons more than hydrogen. So it's going to be the more negative guy. So the more electronegative makes you the more negative one. Because fluorine's oxidation state, it only has 1 listed, and it only wants to gain 1 electron to fill its outer valence orbital, it's going to do that, and it's going to just be -1. If fluorine takes on the -1 charge, hydrogen has to be +1. And the reason for that is because this compound, hydrofluoric acid, is neutral because there's no charge written up here. So you have to have hydrogen have a charge that kind of balances out the fluorine charge to make the overall compound neutral. This is different, and so here hydrogen took the +1 oxidation state. But hydrogen can also have the -1 oxidation state. So let's see when it does that. Okay, so now I'm going to bond sodium with hydrogen. And when I do that, and I look at electronegativity values, we're no longer looking at fluorine. We're only going to look at hydrogen with sodium. Sodium is right here. So now hydrogen's actually the more electronegative one. So hydrogen is going to carry the negative charge, and sodium is going to be the positive guy. So, and that works out nicely because all group 1 elements only ever want to be +1, and so sodium will always be +1 anyway, and the only way this is a neutral compound for this compound to be actually neutral is for hydrogen to be the -1. So hydrogen will actually take on the -1 state in this case because it is the more electronegative element. So just to back up for a second, the reason why hydrogen is positive sometimes and negative other times, this is what's actually happening to our hydrogen atom. So if you look at the hydrogen atom that I drew from earlier right up there, if hydrogen is bonded to somebody who is more electronegative, what's going to happen is the electron on the hydrogen is going to be pulled towards the other element and possibly completely removed. That makes the hydrogen positive because the nucleus still has a positive proton in it. So it will ultimately be positive because you don't have the negative anymore. When hydrogen has the -1 charge, what's happening is instead of, let me just erase really quick. Instead of removing this electron, oh no, I erased my whole atom. So instead of removing the electron, we are now adding another one. So now it's -1 because you have an extra electron. So ultimately, what's making any atom positive is when electrons are leaving it, because electrons are negative, and when it's negative, it means more electrons were added. No protons are being moved in any of these situations. That is in our nuclear unit, which is to come. So that is like nuclear bombs and stuff. We are not removing protons. It's all about electrons moving. So let's practice assigning some oxidation numbers. Okay, so let's practice assigning oxidation numbers for the following compounds in A, sulfur oxide compounds. So the first compound, you have SO. It is a neutral compound because there is no charge written up top here. So we're going to set the whole thing equal to 0. Now, going back to our periodic table, there's a whole bunch of rules for knowing which oxidation state an element has. To simply break it down in like a second, the main rules that will help you with everything else is knowing that fluorine is always going to be -1. For the most part, oxygen's always -2. The only times it's not is times that I won't give you, and that's when it's in a peroxide. So you don't have to worry about that. You could just always think of oxygen as -2. Group 2 elements will always be +2, all of them. And group 1 elements will always be +1, all of them. Hydrogen not included, because hydrogen could be +1 or -1. Everyone else on the periodic table, they can be a whole bunch of different oxidation states. It really depends on who they're bonded with. So we're going to practice figuring out what some of those other guys, what their actual oxidation states are. So let's look at sulfur oxide. And so oxygen, as we said before, is always -2 based on the periodic table right here. So we're going to keep oxygen at -2. Sulfur can have a whole bunch of different oxidation states. It could have even more than the ones that are listed here. So we're going to have to figure out which one it's going to take on. So you're going to just write X, because you don't know what oxidation state it is. And then all you do is solve for X, sulfur's oxidation state, by doing a little bit of algebra. So you want to get X by itself. In order to do that, you need to move the 2 to the other side. So you follow the opposite sign of what's happening. It's being subtracted, so you add it. So sulfur's charge is +2. for the first one. Now let's look at another guy. So here we have SO3. Let's do this one. Again, there's no charge up here, so it's implied 0. So we're going to set the whole thing equal to 0. Each oxygen has a -2 charge, and there's 3 of them. I know there's 3 because there's a little subscript 3 by the oxygen, so I'm going to write -2 3 times. We don't know what charge sulfur has again, so that's our x. So our algebraic statement here is x minus, adding up those 3 -2's is -6, equals 0. Again, solving for x, you're going to do the opposite sign, -6 is being subtracted, so you're going to add it to both sides. So x equals +6. So its oxidation state for sulfur here is +6. Okay, now let's try one that actually has a charge. Let's do this guy, SO4 2-. So this is not a neutral compound. The whole compound gained 2 electrons, which is why it's -2. So it stole it from an element somewhere else. So you're going to set the whole thing equal to -2 now. Oxygen, each one is still -2, and you have 4 of them, so you're going to write -2 4 times. You again don't know what sulfur is, so that's your x. So your statement is x minus 8 equals -2. Again, you're just going to solve for x, and you're going to do the opposite sign here to get this on the other side. So x equals +6. So the oxidation state of sulfur can change. It can be +2, it can be +6. The other compounds, some of them have +4. It really varies, so you have to solve for it. Okay, let's try to just do one problem where we have a few of the other elements. So we're going to try and do the first one, N2O here. Again, there's no charge on this compound, so we're going to set the whole thing equal to 0. You have only 1 oxygen, so just 1 -2. We have 2 nitrogens, so there's going to be 2 x's, because we don't know the charge on any of the nitrogens, and there's 2 of them. So our algebraic expression is we have 2 x's minus 2 equals 0. We're trying to solve for x, so again, our first step is going to do the opposite sign of what's happening here to move this onto the other side. Now you have 2x equals 2. Again, we want to get x by itself. Because 2 is multiplying x, you're going to divide it onto the other side. So now x equals 1. So each nitrogen is +1. And that makes sense, because if this guy is +1 and this one's +1, 2 +1s and -2 together make 0. So we know we did it correctly. So why does this whole thing matter, assigning oxidation numbers? It matters because ultimately you're trying to figure out what kind of reaction you have, whether it's a redox reaction or not. Because if it's a redox reaction, you could theoretically produce electricity from it, whereas non-redox reactions you can't, so it means something if it is. And so, yeah, so if we look at what a redox reaction looks like, you assign oxidation numbers, and here zinc is by itself and it's 0. It changes from reactants to products, so it goes from 0 to +2, and copper goes from +2 to 0. So zinc is losing 2 electrons because it's getting more positive, it's being oxidized, and copper is gaining 2 electrons because it is getting more negative, if you will. It's just losing its positiveness. So it's gaining electrons. So it's being reduced. This number, the oxidation number, is going down. This is different from non-redox reactions where the oxidation number doesn't change for any element from reactants to products. Fluorine stays